This is quantum chromodynamic rules. But they don't occur in neutron stars because they're pretty rare and no one has confirmed that they happen. It's probable, it's possible, no one has proved it yet. But let's start with the nucleus. The nucleus is the center of an atom basically, being surrounded by faraway electrons. We're not focusing on the electrons, we're not even focusing on the nucleus, but we're focusing on these quarks. When we break it apart, we'll have neutrons and protons, and inside the neutrons and protons, there are quarks. Once you try to break a nucleon apart, it will be pulled back in. The quark will be pulled back in, basically. Completely. It's the strongest force in the universe. We're just pulling it back in. It's even stronger than gravity. Of course, gravity is the weakest force in the universe ever. But nobody can ever tell. But if you can break it, something weird happens. You have break the string. But there are antiquarks and quarks forming, and one possibly will crash back into the nucleus. Until this will also fall apart due to the high energy concentration, and that means that you can never actually break the proton apart in regular conditions. Until in the middle, there's a huge gap which is made of creating new quarks. Then this becomes a continuously beam. And then this particle accelerated beam is called a jet. This whole entire thing, they're actually made in particle accelerators. Not over here, but in that big LHC, we're called the Large Hadron Collider, and other large colliders such as the relativistic heavy ion collider, or RHIC. The LHC is much better way to say Large Hadron Collider, and RHIC is a much better name to say relativistic heavy ion collider. It's called RHIC. Basically, this is how the streams are made. Basically, it's made by pulling a quark out of a nucleon and making a chain reaction which goes on seemingly for a long time until you get a jet. That's basically what quantum chromodynamics is. The rules that, however, quarks are held by the strong nuclear force. And here comes a really kind of thing that doesn't make things like quarks and protons are not supposed to be together. That's called the Pauli exclusion principle. The Pauli exclusion principle means that two protons cannot be there at the same time. They have their own degeneracy pressure. Quark degeneracy says that no two can be together. Even though like 3 up quarks are here, there are 3 of them. This one is spinning at the same rate as this one, and that makes it Pauli exclude. But however, there's a solution. All of them have every quark has a different color. That's what they have 3 different charges. One is neutral, one is these 3 charges called colors. They're not like the red, blue, green. Yeah, they're called red, blue, green, but but they're not really red, blue, and green, but just the charge's name. However, when they add up to be white, that's the charge of a proton. The same is for a neutron. Same colors, same white. Okay, so they don't actually have a color. They look more like this in like animations. They don't have a color, but sometimes in a Large Hadron model, you see these colors in the proton model. But in a quark gluon plasma, you see all of these colors usually. Up, down. That's what this means. And green means strange if it's in the charm top button. Actually, it's a proton. And these are some exotic hadrons.